two things that we did in the last class was direct sums and something about diagonalization of linear operators. Okay. So, let us recall what were those. At first, direct sums. Okay. So, suppose you are having a vector space V and let W1, W1, W2 dot 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 Wk be subspaces of a vector space V. Okay. Then first, what do we mean by their sum? This one. Could you just recall what was that? What was the sum? Yeah. Right. Yeah. Okay. So this was just the sum of small wi's, W1 to Wk, such that small wi's are in capital Wi. Okay. And now such a sum. So this is just a sum. We do not call it a direct sum yet. Okay. So we call the sum of W1 dot Wk, that is what we have just written up here, a direct sum of these spaces if every element or every vector in W1 or dot Wk, the sum actually, every vector in the sum can be written uniquely as a sum of the elements Wi in Wi. That is, every element has such a unique expression. Okay. So let us see why this matches with the definition that we saw earlier. What was the definition that we saw earlier? We will call it a sum of vector spaces. Okay. And then we call it a direct sum once these are independent, right. Now we said that we call it a direct sum if every vector in this has a unique representation in terms of this. So Vishesh, can you just explain why this is true? I mean, this is the first exercise actually. So the first topic is going to be direct sums, and the exercise that we give about direct sums is going to be rather simple. I mean, it will just follow from the definition that you are going to use here. Okay. So yeah, now what we are trying to prove? We are trying to prove this claim. That is, it's a direct sum. We call this sum a direct sum if and only if every vector in this Minkowski sum in this has a unique representation like this one. Okay. So please proceed to prove. Tell me how to. So this is a claim, and this is actually the first exercise which we, I mean, if you do it, it will be clear that you could recall the things what we have done in the, I mean, how we defined the direct sum in the previous class clearly. Indeed, a direct sum, you get that this representation should be unique, and the opposite, we said that is if and only if. I mean, these are equivalent definitions. Opposite means that now you know that all these expressions, all such expressions are unique. Now you are going back. So you are trying to prove that the only expression that this can give, I mean, the only expression like W1 plus W2 plus dot Wk equal to 0 will have all the components 0. So how would you go about that? Yes. So now you are having the assumption that each of the vectors can be written uniquely. So in particular, if W1 plus dot plus Wk equal to 0 has a unique representation, and you know that this is of course a representation, right, because 0 is on the in all the subspaces. So this is already a representation of 0. Okay. So if the representation is unique, then all of these are going to be the same. Okay. So yeah, this was actually a really easy exercise. Okay. And so is going to be the exercise that you are going to see in the first problem of the test today. Okay. And here you need not even require basis, because it also follows directly from the definition of direct sums. Okay. But your way is perfect as well, okay, because you are using the uniqueness of the things. And otherwise, you can say that W1 plus dot 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 plus Wk. Now what I am doing, I am assuming it's a direct sum, and I am trying to prove that every expression should be unique. Every vector in this sum should be uniquely expressed without using the basis. Okay. So you could write that. Suppose this is true, okay, and then take them just to the other side. Okay. W1 minus W1 dash plus dot 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 plus Wk minus Wk dash. This is equal to 0. Okay. And since we are saying that it's a direct sum, that is now the assumption is that it's a direct sum. So we will have that each of these components are 0, right? Because W1 minus W1 dash is in W1, Wk minus Wk dash is in Wk. Vishesh, is it all right? Okay, because this is just a linear combination of the things that are in Wk, right? Are you with me, Vishesh? Okay. So that just implies that Wi equal to Wi dash for all I. Okay. All right. So that's about direct sums, and let's now recall the things that we have done till now on diagonalization. Okay. So T from V to V, let it be a linear operator. Okay. And then T of what we did, we said that if there exists an eigenbasis, that is, if there exists a basis made up of eigenvectors, then what we have, that is, suppose this is V1 dot 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 Vn is a basis of eigenvectors, then this would be just lambda V1, sorry, lambda 1 V1 dot 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 lambda n Vn, not all distinct, not all necessarily distinct. Okay. So this will be this, and then if you want to just represent T in terms of this basis B with a matrix, how would this matrix look like? Yes, a bit louder. Yes, so it's a diagonal matrix, right? And let's recall when do we call a matrix diagonalizable? Sorry, linear operator or diagonalizable. Well, as well as a matrix diagonalizable. Diagonalizable linear operator if there exists a basis B with respect to which the matrix of the matrix say A of the linear operator here T is diagonal. Okay. So then we say that the linear operator is diagonalizable. Okay. And in terms of matrices, if a matrix is similar to a diagonal matrix, we call the matrix also diagonalizable. These two things are related because you see, I mean, if you change the basis, the matrices change by conjugation, right? So A goes to a matrix similar to A, right, Vishesh? So that's why if there is some basis with respect to which the matrix of representation is diagonal, that means this matrix A, for some arbitrary basis, would be conjugate to that matrix, which is a diagonal matrix. Okay, so it should be similar to the diagonal matrix. Okay. So if for some basis A is similar to a diagonal matrix, or if for some basis this matrix has, sorry, this linear operator has a representation with a matrix which is diagonal, we say this matrix is diagonal, sorry, this linear operator is diagonal, or that this matrix, whatever matrix it is, which is representative with respect to some basis, is diagonalizable. Okay. And let's write it down here as well. Where here? So that's the definition of a diagonalizable linear operator, and hence we also, I mean, this induces the definition of a diagonalizable matrix is a matrix similar to a diagonal matrix. Okay. Lambda is not necessarily or distinct. Okay. Similar to just means that this and this are conjugate. Okay. Conjugate with, I mean, A is just P, this P inverse. And why diagonalization is important? It has lots and lots of applications, but in particular, if you have, for example, if you want to say take the power of a linear operator, I mean, often you would consider polynomials in linear operator, that is a n t n plus a n minus 1 t n minus 1 plus dot 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 a 0 I, okay, things like this. Perhaps you have already seen one problem involving these ones. Okay, so you see here, I mean, in such cases you are taking powers of the linear operator. Okay, or if you are considering in particular basis, then you are considering like a n a power n a n minus 1 a power n minus 1 plus dot 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 plus a 0 I, things like this. Okay. And what you require is that to take power of a matrix, that is in terms of, I mean, if you want to take power of a linear operator, this just means that you want to take the representative power of the corresponding power of the representative matrix. And how do you do that? Okay. Yes. Yes. So, well, to do this, you have to multiply the matrix. That's right. But suppose your matrix has a huge dimension. Okay. So then, in particular, if your matrix is diagonalizable, it's quite easy to raise it to power. Okay, because this would be then just P D P. How do we write P inverse P D? P inverse dP, right? We took the inverse in the front. Okay, and then P inverse dP, and so on. P inverse dP. Okay, and what it boils down to, you see, once you open the bracket, this P inverse all gets cancelled, right? So you get at the end P inverse d power n P. Okay, I note that if it is a diagonal matrix, raising it to a nth power is rather simple. You just raise the diagonal things. I mean, so this one would be just similar to the nth power. The diagonal entries will just replaced by the nth power of them, because when you multiply diagonal things, the diagonal elements, the corresponding diagonal elements just get multiplied. So that's how, I mean, it's rather easy to raise matrices to nth power if it is diagonalizable. And how complicated raising a linear operator to a power may be, you can see it from here. So suppose it's a simple linear operator on R2, and suppose what it does, it rotates and contracts the vectors. Okay, so you have, say, this one first, it rotates it a little bit by some particular angle and contracts. At first it is going here and it's contracting, but so V goes to this point and then it will get rotated a bit here, okay, here, and contracting, and then a bit rotating here and contracting, okay, and so on, right. So that is the right picture. So this goes here, goes here, goes here, and it goes on, okay. So if you want to visualize it, how exactly such a thing works, such a power of a linear operator work, if you know that the operator is diagonalizable, it's quite easy to write it down. What such a thing would be, such a polynomial, the effect of such a polynomial would be on the vector that you are taking. Okay. So you can compute its image. All right, now let's come back to what we have done in the earlier class. So this thing that we can, a matrix, a linear operator is diagonalizable if and only if it has an eigenbasis, that is a basis made of eigenvectors. This, I think we have also seen it in, not in the previous class, but the previous to previous class, right? That if TB is equal to BA, A should be diagonal, and also vice versa. If A is diagonal, each of these ones would be eigenvectors. Why? The same thing, right? You have this basis T V1 dot 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 Vn, and then you are having again this basis here, because TB is equal to BA, and here you are having some diagonal matrix A11 dot 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 ANN, right? Okay. Note that means TV1 is A11 V1. It's an eigenvector. Okay. TVN similarly is ANN Vn. That well, maybe I write it down here, which is that would be actually helpful. So we are proving a theorem, and I am just recalling that some part of the theorem we have already proven, though we have not written down as, in the form of a theorem. So 10 years from now, if I would like you to remember a theorem, this is going to be this. Okay, so this theorem should be the takeaway from linear algebra course. If you forget everything, at least remember this one. Okay. So theorem. Let T from V to V be a linear operator. Suppose it's a complex vector space. Okay. This we would require at the end. Okay. Then the following are equivalent. Okay. So what are these? 1, T is diagonalizable. 2, T admits an eigenbasis. Okay. So this equivalence we are talking about till now, that we have seen this earlier, and also this one, that if lambda 1 dot 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 lambda k are distinct eigenvalues of T, then E lambda 1 direct sum E lambda 2 dot 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 E lambda k. Well, in the previous class we proved that these are independent spaces, right? So their sum is actually a direct sum. Now, if the eigenbasis should exist, what it should mean? That this direct sum is equal to V, right? So, these three are and actually that would imply, so fourth part as well. So, by the way, this is the thing from which you will get the second problem today, and a rather simple one. It will not look so complicated. It is a very simple problem. You have just to apply this theorem. Okay. 1, 2, 3, 4. Yes. So, the sum of the geometric multiplicities of the eigenvalues of T is what? The dimension of E, right? And 5, the algebraic multiplicity. Okay, wait a minute. For each root, because otherwise it may mean something different if we write the multiplicities first. For each eigenvalue, lambda of the algebraic multiplicity of lambda is equal to the geometric multiplicity of lambda. Okay. The algebraic and geometric multiplicities are the same. So, till now what we were recollecting from previous class was the equivalence of these two things. T is diagonalizable if and only if T admits an eigenbasis. Okay. Shivam, is it fine that these two are equivalent? We have seen it in previous class. Okay. And this one, the independence of this, we have also seen in some previous class. Now, a question about this. Okay. So, suppose you have a set of distinct eigenvalues of T. Okay. So, this is a practice problem as well for the last one, okay, from to check your understanding of this as well as direct sums. Okay. So, suppose lambda 1 dot lambda k be a set of distinct. So, this is an exercise and you will do it immediately. Okay. Eigenvalues of T such that E lambda 1 direct sum dot 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 direct sum E lambda k is equal to V. Can T have an eigenvalue lambda not in this set lambda 1 dot 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 lambda k? Can there be an eigenvalue of T outside this set? No, you can use whatever you have done in the class till now. Okay, no, actually no, don't use the theorem. So, just use whatever we have done till now. Okay, that is we showed that these are independent. Okay, just use that fact. Yes, yes. Lambda is an eigenvalue of T, suppose, right? That's in V. sure, not one of those, but it should be a linear combination of this, but that is not possible. Why? So you have yes, Anisha. So you exactly, that's the thing. So suppose V is in E lambda, right? And this E lambda is supposed to be independent of all of these things. Okay. So now, if E lambda is a subset of the span of this, that cannot happen. I mean, E lambda and this are independent, right? So this can be a subset of this if and only if this is 0. Your previous question. Okay. So unless it's 0, that means, I mean, since this unless it's 0, then unless it's 0, what will happen? So E lambda 1, suppose then we will have an expression like, say, E lambda 1 plus dot 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 plus E lambda k, right? Take V to the other side. So you have then E lambda, I mean, this linear combination minus V, which is equal to 0. But all these are distinct eigenvalues of T, right? And you have shown that the eigenspaces corresponding to distinct eigenvalues are independent. So that means if this is equal to 0, each of them has to be 0. In particular, V cannot be an eigenvector. All right. So there cannot be a lambda which is outside this set. Vishesh, the argument is it clear, or so is it clear to everybody? Abhinav, Abhurtha? No. Okay. Thank you very much for mentioning that. Okay. So suppose there exists some lambda which is not in this set. Okay. Now in the previous class we have shown that if the eigenvalues are distinct, for example this set lambda 1 to lambda k and lambda, this is a set of distinct eigenvalues, right? The corresponding eigenspaces should be independent, right? Now if V is in E lambda, which is a subset of V, and we already have that this direct sum is V, that means that every element in V is expressible as a linear combination of elements from these ones, E lambda 1 to E lambda k. So in particular this V, we could also write it as E lambda 1 plus dot 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 E lambda k, and then take V to the V inside. Okay. So this is a linear combination of things from this sum E lambda plus E lambda 1 plus dot 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 plus E lambda k, right? But in the previous class we saw that if these are linear, these are distinct, this E lambda 1 dot 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 E lambda k, these are independent. Okay. So such a thing can be equal to 0 if and only if each of them are 0. Okay. In particular, V should be 0, but V was supposed to be an eigenvector in E lambda. So V was in E lambda minus 0. Okay. Yes. Sure, sure. Sure, sure. Indeed, yeah. Perfect. Yes. Wonderful. Yeah. That's a beautiful proof as well. Okay. So yeah, you can directly apply what Naomi just said. That is, you can start with a basis. You can see the matrix representation of T with respect to that basis. Then the characteristic polynomial of that matrix consists of only this as the roots and not lambda. Okay. So that's perfectly. I mean that's perfectly. That's an argument, a perfect argument which proves this as well. Okay. Without resorting to independence of spaces. Okay. So this is perfect. The solution, and now, so we are done with this part. Okay. Now the next one, that the sum of the geometric multiplicities is dimension of V. Why this? Just 1 minute. Let Vishesh finish this, because you are looking a bit dazed. I am not sure whether you are with the class or the argument. So I'm just asking why the sum of the geometric eigenvalues of corresponding to distinct eigenvectors of T is going to be the dimension of V. So this one. we have shown that these are equivalent. Okay. Now we, I mean, it's fine if you could show that 4 is equivalent to any of them. Choose your favorite and show that this one is equivalent to that. Or you can show that one of them implies this one, and this implies some another one of them. That's also fine. Yes. So we are summing the geometric multiplicity at first. What is the geometric multiplicity of a root of an eigenvalue? No, that's not. The geometric multiplicity of a root lambda. Yes. So geometric multiplicity is the dimension of what? Right, the kernel of that. Yeah. Kernel of t minus lambda I. Right. And the kernel of t minus lambda I we denoted here. Which one is that? Sidem? Yeah? Very good. It's E lambda. So this is just E lambda. Okay. This is the eigenspace. Okay. And we are talking about the dimension of the eigenspace. That is the geometric multiplicity. Okay. And now the sum is equal to the dimension of V. This is just this one, you see. Because we saw earlier that if we are talking about direct sum of a set of subspaces, take the basis of each of the subspaces, just put them one after another, that forms a basis of V. Okay. And that was an if and only if condition. So you can choose a basis for this, you can choose a basis for this, you can choose a basis for this as well. You can put all of them together and you get a basis of V, right? Now, what is the coordinate of the basis of this? The geometric multiplicity of lambda I. What is the coordinate of the basis of this? The geometric multiplicity of lambda 2, and so on. Okay. That gives you the sum to the dimension. Okay. And this is an if and only if condition because if the sum of the geometric multiplicities is dimension of V, that means dimension of V is equal to the sum of the coordinates of their bases, right? And that means that you have enough vectors here. At first you know that they are independent. So they are, I mean, forget about whether this is V or not, but you can always write it in this manner. Okay. Given a set of distinct eigenvalues, you can always write this sum. It may not be equal to V, it could be something smaller, but this expression has, I mean, writing things like this is not a problem as long as lambda 1 to lambda k are distinct, because these are independent. We showed in the previous class. Now, if the sum of the geometric multiplicities is equal to the dimension, that means there are enough vectors in this direct sum, enough linearly independent vector to make a basis of V. Okay. So this will also imply this one, right? So this is then done as well, trivially from that expression. Okay. Now the last one. Okay. Yes. Okay, sure. So at first, wipe this out and just concentrate on this expression. Suppose lambda 1 to lambda k are distinct. Can we write this expression at all? I mean, this direct sum. We can, because these spaces are independent. This was the last theorem that we proved in the previous class. Okay. Now suppose that this is equal to V. Okay. What does this mean? If you put the basis of this, this, and this together, that would form a basis of V. That was also another thing that we left as a homework, but we gave complete hint. I mean, how to actually it was a easy homework following just from the definition of direct sums. Okay. So this one would mean that putting their bases together would make a basis of V. That's all you require for this. Because this is just saying that if you sum the cardinalities of the individual bases, you get the cardinality of a basis of V. All right. So that's it. I mean, this actually is a two-way proof. It implies, I mean, from here you go here, and also you can go back, because that just means that the dimension of V, the cardinality of a basis of V, is the sum of the cardinals of the basis here. Okay. So that's it. And the last one. Okay. And once we are done, we will have the time for a very small exercise. But this theorem is what class do you have after this? You have a class or not? No? Okay, that's great. So we can have like a few minutes more to finish the exercise that we will do. And this theorem is a beautiful theorem, because from this lots of very nice exercises could be made, okay, on diagonalizations. Gayatri, yes. Yeah, please, please. So we just show that the last two propositions written on that board are equivalent. Okay. So proof that 4 and 5 are equivalent. And this would be rather simple, because you know what is the sum of the algebraic multiplicities? Suppose, yes, right. So sum of the, at first we start with what we have shown earlier, that is algebraic multiplicity for the ith eigenvalue is greater than the geometric multiplicity for the ith eigenvalue. Okay. Sum over I. Okay. What is this sum? Dimension of V. Okay. And what is this sum? If you are having this one, then what is the sum of the geometric eigenvalues? What is the sum of the geometric multiplicities? Yeah, that was the fourth. Okay. So this is going to be the dimension of V. So this is at first 4 implies 5. Okay. Yes, Vishesh. What is the definition of algebraic multiplicity? Root of the? Right. And what is the degree of the characteristic polynomial? I said that this we use at the end. Okay. That the field is algebraically closed, that we use now here. So, and given any field, you will have, you can construct an algebraic closure over that, even a finite field. Okay. Now a small question for you, that is, you know the field of rationals, you know the field of complex numbers. The question is that whether, so at first, what is an algebraic closure of a field? It is just a detour, it is not directly related with what we are doing now, because we will do with C and R, but by algebraic closure of a field, we mean a field in which every equation over the base field has a solution. For example, take any equation with coefficient from R that will have a solution in C. All kind of equations that you can write with coefficients from the base field. Okay. All kinds of polynomial equations. Okay. And then the question for you is that whether, well, and wait a minute. And every element in an algebraic closure is root of some polynomial in the base field, some single variable polynomial in the base field. Okay. Now the question for you is, so suppose you have a field L which is an algebraic closure of a field F. Okay. That means every polynomial in F, I mean with coefficients from F, will have a root in L. And every element in L would be root of some polynomial equation with coefficients from F. Okay. Now the question is that whether C is the algebraic closure of Q or not. C is algebraically closed. Any anything, any equation, any single variable equation, I mean, take any polynomial in single variable, make it equal to 0 with all the coefficients where all the coefficients are coming from C. Okay. Yeah, I am just saying that C itself is algebraic closed. I mean, you can. So now the question is that is Q an algebraic closure of C? Yes, and whether that's true or not. Yes, counter examples. Yeah. So the question is that whether C an algebraic closure of Q or not. That is wonderful. Any transcendental number. Take pi, for example. It's not a root of an algebraic equation over Q, right? So this we denote by Q bar, which is a much smaller field than C. Okay. C is of course the algebraic closure of R. Okay. Well, that was a detour. Let's come back to the complex numbers and finish this argument. Okay. It's not bothering us, so we can keep it there. Yeah. So dimension V is the sum of the algebraic multiplicities then, because it's the degree of the characteristic polynomial, right? And this is larger than or equal to the sum of the geometric multiplicities, which is equal to dimension of V, because we are assuming fourth, or we are assuming this one. Okay, we are already saying that the sum is equal to dimension of V. Now, note that if there were a single strict inequality here, can this be true? It cannot, right? So for each of the i's, this has to be an equality. For the, I mean, on the left and on the right, we are having dimension V sitting there. Okay. So that implies that the arithmetic, algebraic multiplicity of the ith eigenvalue is equal to the geometric multiplicity of the ith eigenvalue, right? Now the reverse. Suppose this is true for all of them, okay, and then consider this sum over the i's. Okay, so this would imply again. Now this was the proof from 4 to 5, and now we are going back. Okay, so now suppose this is the assumption in fifth, right? That algebraic multiplicity is equal to the geometric multiplicity for all i's. Sum over I. Okay. Now this one is the dimension of V by definition, and that implies that this sum is equal to the dimension of V. So we're done. That was the assumption here. Okay, so yes, we are assuming the field to be algebraically closed. Exactly. Yes. Yeah. For things which are not algebraically closed, no. No, that's why we declared this. Okay, that's why. If you are starting with algebraic closed field of vector space over C, for example. Okay, and this theorem is going to be rather important also when we talk about spectral theorem, because we'll use it as a step to go to the spectral theorem. Okay. I mean, whenever we talk about diagonalization of a matrix or a linear operator, we are going to use this theorem. Yes, Kaushik. Which one? No. For example, I mean, if the field is algebraically closed, it's not. For example, consider this one. We took this earlier also, right? That consider things like this. Okay. This is not a diagonalizable matrix. Okay. Because you can read off the eigenvalues from the diagonal. Okay. But this is not equivalent to 1, 1, that identity matrix. Okay. All right. So just a small exercise. Actually, Kaushik, your question leads to a very nice thing. If a matrix, so So we know now how to identify diagonalizable operators or diagonalizable matrices. But what if the matrix is not diagonalizable? Okay, then you can always make it an upper triangular matrix or a lower triangular matrix. That is, you can still read off the eigenvalues from the diagonal, only it will not be zeros on both sides of the diagonal. Okay. And in fact, how much you can reduce this upper part, that is so you know that it is not just a single diagonal, but how much you can reduce it will be given to you by Jordan blocks, okay, that you learn later in linear algebra 2. Okay. And you can, it turns out that you can reduce it all the way up to just one line here, just one line above the diagonal, and that would be, you can also tell what the possible entries of that line would be. It would be a set of ones or zeros. Okay. If it is diagonalizable, all as 0 here. If it is not, you will having a set of ones here, and then maybe a few zeros, then a set of ones, and things like this. For example, this one, what we have written here, things like this would be called Jordan blocks. Okay. So lambda, just a single lambda, is a 1 cross 1 Jordan block. This is a 2 cross 2 Jordan block, and you can imagine what a 3 cross 3 Jordan block will be: lambda, 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 and 1, 1. Okay. So each Jordan block will correspond to geometric multiplicity 1 and algebraic multiplicity as many things are there on the diagonal. Okay. Okay, so Jordan canonical form is an easy way to represent the matrix from which you can immediately read off not the eigenvalues only, but both their algebraic and geometric multiplicities. Okay. But we do not go into that. Proving that a matrix can always be represented by a upper triangular or a lower triangular form. Say for a basis it has some upper triangular form. Just reverse the order of the matrix. You get this to be lower triangular. Okay. And well, the proof of this could be done by induction. It's not very difficult. So maybe I wipe. I would like to wipe this one. Let the theorem remain there, because I'm going to discuss just an application of this. So can I wipe this part, this board? Thank you. Bitan, you look sleepy. Are you with the class, or are you falling back? At least look at the statement of the theorem. You can look at the proof later in the videos. I hope I will post it very soon, but not before the, it's of no use actually posting it before the test today. I'm anyway saying what are important for the tests, and you won't have time to look at it anyway. So what I was saying, at first, any matrix. So this is not yet the application. I'm just talking a little bit about what happens if the matrix is not diagonalizable. Okay. So these are small. Well, you can complete the proof at home, but the thing is that any matrix over C is similar to an upper triangular or lower triangular matrix. It's equivalent. Matrix. Okay. And proof, just, well, the proof should be done by you. It's a homework, but I can give you some hint. Start by induction. Okay. So it's not a proof, it's a hint. Induction. For 1 cross 1, it's trivial. And for others, you can assume that you know it for n minus 1 cross n minus 1. And then you just have to go to n from n minus 1. So suppose V is an eigenvalue of your matrix. AV is equal to lambda V. And then, or you can imagine that this matrix represents a linear operator somewhere, and you can also write it as T v equal to lambda v, and then the matrix of T with respect to this, well, which basis you want to expand V, I mean extend V to full basis of the vector space on which T is operating. Okay, so extend V to a basis, etc. Okay, extend to a full basis. The matrix of T with respect to that basis would look like lambda. We did this trick earlier in the previous class, and all zeros here and some D here. Okay. And by the induction hypothesis, we are assuming that this D could be, I mean D is similar to some upper triangular matrix. Okay. So if P inverse dP is upper triangular, then this is a bad way to write, but how to write? Okay, is upper triangular. Then can I wipe this corner? Okay, thank you. If P inverse dP is upper triangular, all you have to do is to consider this matrix 1 zeros here, and here P, call this your new matrix, say P hat. Let P hat be defined in this manner, and then use P hat in the role of P inverse here. So basically you have this matrix here, now do P hat inverse this P hat there. Okay. That would give you a diagonal, not diagonal, an upper triangular form for D, and this one was already lambda and all zeros here. Okay. So that's how you complete the induction. Okay. Now complete so that was just a hint, complete the details at home. Okay. And now about an application of this in finding whether linear operator T is diagonalizable. As I mentioned, it has, I mean, many beautiful problems could be formed with this. So here is one for you. Write it down. And the problem that we are going to ask in the exam today is not even nearly going to be as hard as this one, but I hope you can also do this in the class. It's just one small intuition and you can do it. So maybe I wipe this part, the last board. Okay. Suppose you have a linear operator T from R5 to R5, okay, such that the characteristic polynomial of T such that if, wait a minute, T is a linear operator from R5 to R5, and let F be the characteristic polynomial of T. Okay. Suppose f of 1 is equal to f of root 2 is equal to 1, okay, and f of minus 1, no, not f of minus 1, excuse me, f f of 1, no, sorry, not root 2. Excuse me, f of 1 is equal to f of e, the base of the exponential function. Okay. So, suppose f1 equal to fe equal to 1 and f of square root 2 equal to f of pi equal to minus 1. Okay. Prove or disprove T is diagonalizable. Prove or disprove T is diagonalizable from this information which we gave you. I am now clearing up the middle part of the board. I hope you noted down the theorem. It's not? Why? Why? No, think again. I mean, whatever you say, yes or no, just justify your answer. What information do we have about the characteristic polynomial? What is its degree? 5. And the first coefficient? It should be 1. Okay. So how does its curve look like? Well, you know something about these ones, f1, fe. Okay. So at 1, its value is 1, right? At e, well, at first let's mark this 1 e root 2 and pi on the line. Okay. Well, that was right. Exactly. So 1 here and root 2 here. Root 2 is about, I mean, a little, so in the neighborhood of 1.414, etc., etc., not exactly 1.414, of course. And then you have e, then you have pi, right? So what you have here, f of 1 is 1, f of root 2 is minus 1, f of e is 1, f of pi is minus 1. So your so what analytic tool are we using? Intermediate value theorem. That's great. But how many roots do you see here? 1, 2, 3. Yes. Wonderful. Yes. So here should be a root there. Wonderful. You see, it cuts between 1 and root 2. It cuts between root 2 and d. It cuts between e and pi, and it cuts between pi and infinity. And here it cuts between 1 and minus infinity. So all the roots are distinct. Okay, all the eigenvalues are distinct, right? Yes, and so it has 5 linearly independent eigenvectors because the eigenbases are independent, right? Okay. Which one? These ones? Because the characteristic polynomial ft is e power 5 plus big O of e power 4. This term dominates, and and you can treat them. I mean, this is bounded by some constant times t power 4. Because ft is determinant of what? How was it defined? The characteristic polynomial of a linear operator. No, we didn't define it in that manner. In the last class, we also proved a theorem, and while proving the theorem, we mentioned that why we are making this convention of putting Ti earlier. We wrote it as Ti minus A. A is the matrix of representation of T with respect to some basis. Okay. And why do we do this? Because we want to make the first coefficient monic, because we will have then information, precise information about 3 of the coefficients. The first is monic, the second is the trace, that is the sum of the eigenvalues, and the last one is minus 1 whole power n, the determinant, product of the eigenvalues. And in between, actually, you can also write them down. Those will be symmetric polynomials in the eigenvalues. Okay. So in particular, the first coefficient is t power 5 or t power n. Okay. So since it's a odd number here, as t goes to minus infinity, it will go to minus infinity as well as t goes to positive infinity, and there you do not require whether the power of t is positive or negative. It will, I mean, if t power, for any t power n, as t goes to positive infinity, this goes to infinity, right? So therefore, this will cut somewhere between, because this was minus 1 and this is going to infinity, by intermediate value theorem, it cuts somewhere in between, right? So therefore, f has 5 distinct roots, and since e lambda 1 plus dot 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 plus e lambda 5 distinct roots, say lambda 1, lambda 2 to lambda 5. Now we know that this is equal to V. Why do we know this? Exactly, yes. Okay, so because the geometric multiplicity of each root is greater than or equal to 1. Okay, and we saw that if the geometric multiplicity, I mean, and it will be bounded above by the algebraic multiplicity. And what is the algebraic multiplicity of each of these roots then? 1, because each of, I mean, it has 5 distinct roots and it's a degree 5 polynomial. So no root is repeated, right? So each of the algebraic multiplicity is also 1, okay? And that means this is an equality. Okay? So the algebraic multiplicity and geometric multiplicity of each of the roots are the same, and therefore the matrix is diagonalizable. Okay? And you also have this one is upper 5. But you can just, I mean, argue from here that the algebraic multiplicity and the geometric multiplicities must be the same, and we are done. Okay. All right. So that was a practice problem, and yeah. So one of the problems from this part, of course, you need not use algebraic or geometric multiplicities because that we did at the end today. Okay. But nevertheless, the first 3 parts would suffice. Of course, you know what is geometric multiplicity or what is algebraic multiplicity. So the definitions you could use. Okay. But these are equivalent, we just proved today. But nevertheless, earlier what we have seen is that a matrix is diagonalizable if and only if it admits a basis of eigenvectors. Okay. And that if lambda 1 to lambda n are distinct eigenvalues, the corresponding eigenspaces are independent. So yeah, you can use them, and as I mentioned, the problem is going to be rather simple. I mean, both of the problems on direct sums and on diagonalization. Okay. So that's all for this class. Wish you all the best for the exam. And one more thing I must say, if you recall, in the first class we mentioned that in the next period, I mean just after the puja, I am not there, so there will be 3 consecutive class tests there. So your puja break is not exactly a break, but if you're falling back from the class, please use it, watch the videos, do the exercises from our team, and you have, I mean, now plenty of tests also. You have collected the test problem from the previous tests, as well as your seniors have, I guess they shared their notes and the problems they made with you as well. So you have plenty of things to practice with, but first be at par with the class. Okay, so if you're falling back, use this time to catch up so that the rest of the tests are goes well and your semester examination is very good, the best that you can give. Okay, so that's all for you. On 6th, on 8th, and well, on I mean, there should have been 2 classes on 9th of October, but there is not, because Shomanlo sir said that he will shift one of the classes. So he wants to take the morning class on 9th because he is not there on 8th. Okay, so instead of analysis class on 8th, there will be another exam. Okay, so on 6th there is an exam, I mean small test. 6th, 8th, and 9th, there will be 3 consecutive tests. Okay, and the syllabus would be what we have covered till now. Okay, but for today, the syllabus is very small. It's just direct sums, the definition of direct sums actually, and this theorem, the fast 3 part.